A minus MA V plus, this is the minus sign, VIA is equal to MB VFB minus MB VIB. All right. Again, alphabet soup, we're going to narrow it down now, and there's a point to it. Mass times velocity obviously shows up 4 times here. That's too much to write. Physicists at this point said, oh, God, can't we come up with something better? So they came up with the letter P, and that's just going to be mass times velocity. So my equation becomes negative P final of A plus P initial of A equals P final of B minus P initial of B. Almost there. All right, so at this point, physicists look at that and they're thinking, oh, wait a second, something might be here. Let's get all the ones that have I on one side, all the ones that have F on the other side. So get all the initials together, get all the finals together. So I'm going to take this initial here and I'm going to add this to both sides. I got my final here, I'm going to add that to both sides. So over on my left-hand side, I got my PIA plus PIB. On the left-hand side, right-hand side, I have PFB plus PFA. Yeah, that's incredible, isn't it? All right, so what does this all mean? Whatever this thing P is, if I add up my total initially, so I add up what it is for A and what it is for B initially, that is equal to what I have finally. Whenever I have the sum of something that's initial is equal to the sum of something final, we have a conservation law. It's supposed to be an R. And in this time, it's conservation of whatever P is, and we just can't keep calling it P. It has another name. This is momentum. And so this is the math representation of conservation of momentum. So if I look at the total momentum, if I got 2 objects colliding with each other, if I look at that total momentum beforehand and the total afterwards, they are the same. Why this is critical, or why this is very important, is the conservation law holds true when you're working on your Nobel Prize winning work. Conservation momentum is still there. Also, while they're interacting, their normal force that they exert on each other is 0 to start with because they're not touching each other. They hit, it goes from 0 to something big, and then they separate, and then it goes back to 0 again. If we try to use F equal ma to try to do that, it'd be very difficult because the force changes. The nice thing about this is we don't care what happens while they're interacting. You just look at before, after, that number is the same. Questions to hear? All right. So that's conservation momentum. P is momentum. This right here, this F times T, that's impulse. And if you follow the track down here on the right-hand side, we have this impulse is equal to that right there, which is the change in momentum of B. So the other formula is that impulse which is force times time, is also the change in momentum. So So which formula do you use? Do you force times time, or do you change your momentum? Well, depends on what you're given. So chapter 6 is the one we're doing now. That's momentum, impulse, work and energy, chapter 7. All right, so I take this marker. What is its velocity relative to us? Somebody said it.
0.
Okay. So what is its momentum?
0.
Yeah, it's mass times velocity. If velocity is 0, the momentum is 0. I drop it. Did the momentum, while it was falling, did the momentum stay 0?
No.
Chikara?
Said no. No.
All right. But how is momentum conserved if the marker is falling and the momentum didn't stay 0? But why did the marker fall?
There's a change in velocity.
Okay, there was a change in velocity. What caused the acceleration?
Gravity.
What object caused the acceleration?
Oh, your hand, like from dropping it into the ground.
Once I let go, I had no connection with it. No Jedi powers.
The weight of the marker.
Pardon?
The weight of the marker.
What caused the weight of the marker?
Acceleration.
What's causing the gravity then? Forces require 2 objects. What's the other object? Yeah, the Earth. So, as the marker fell, if momentum is conserved, the Earth would have had to have moved up. Now, did we notice the Earth moving up? No, we don't have equipment that can actually measure that. Momentum seems to be conserved in all the cases that we can deal with, so we have to assume that it also applies there. But I figured out if I jumped off the table and I fell with my 200 and what pounds of weight, the Earth would move up about the size of a nucleus of an atom. Not particularly noticeable. So this gets into this idea of, yeah, in the case of it's falling, yeah, momentum's conserved, bring the Earth into it, but if you're not looking at the Earth, momentum doesn't seem to be conserved. And so we have this idea of momentum is conserved in a closed system. And a closed system means that you are analyzing all the objects involved. So if we analyze the Earth and the marker, momentum is conserved. If I looked at just the marker, that is an open system. So momentum is not conserved in an open system. Open system means there's some outside influence. If I'm looking at just the marker, the Earth is pulling on it, that's coming from the outside. All right. Questions here? All right, so let's actually do some numbers. I have a 3 kilogram mass heading to the right at 4 meters per second. I have a 2 kilogram mass heading to the left at 5 meters per second. So this is before. So let's just start out with just the before. What is the momentum? Again, that's my equation right there. What is the momentum of the 3 kilogram mass? Why? What's that 4 meters per second and 5 meters per second? Did you get 10? Oh, you're doing the 2 kilogram mass. Okay. So what's the momentum of the 2 kilogram mass? 10 what? Absolutely. So the momentum here, mass times velocity, which is 2 kilograms, times 5 meters per second, which is 10 kilogram meters per second. There is no nice 1-letter unit for that. You can make up one, but make sure you label it. What I'm gonna do is, just because I don't feel like writing that much, is I'm gonna put over here in the corner, and since we don't use a letter that we're already using, so I'm gonna define a capital D as a kilogram meter per second. With that defined, I can then write this as 10D. D for Descartes. He did some initial work on that. Descartes was looking at momentum while Newton was looking at forces. Pretty sure they overlap. All right. So when Stephanie told us 10, she established something here, but let's see how many people caught that. What is the momentum of the 3 kilogram mass? Sorry, say it again.
12 kilograms meter per second.
Close. Now, if I'd heard that first, you would have been right, and Stephanie would have been wrong.
You mean the same thing but negative?
Yes. Because we're dealing with vectors here, direction matters. And because I heard Stephanie first, she established it that way as positive. Because that's positive 10, so momentum and velocity are in the same direction, so. That got established very quickly as the positive direction. So therefore, the momentum here, I'm going to put this P2 initial and P3 initial, is 3 kilograms times -4 meters per second. -12 Descartes, or kilogram meters per second. Again, Descartes is a unit that I have made up. That's why I wrote it up in the corner. It is not an established one. I went to a lecture once where the person was advocating the capital B for Becquerel. I can't remember the guy's name. And it doesn't even have to be a letter. I've had students in the past just make up a set of squiggles that they used over and over again. Now, given that to the left is positive, what's the total in momentum beforehand? What is the total initial momentum? Yes, you just add them up. So P initial is -2 kilogram meters per second. All right, questions how we got to the total momentum beforehand. The biggest mistake that students make is they forget that they're in opposite directions, so that's going to be a negative. All right, so now let's say that after the collision, 3 kilogram and 2 kilogram stick together. As a side note, this is known as, or I will refer to it as, a perfectly inelastic collision, which I will often just shorthand to PIC. Perfectly inelastic collision, the perfectly inelastic means that they're sticking together, collision, they hit each other. What is my total momentum afterwards? Somebody go for it.
0.
Ooh, not 0.
Would it be 2? Positive.
Ooh. But you're closer.
-2.
Yeah, -2. It's the exact same thing. That's the whole idea of conservation momentum, is whatever my total is beforehand, that's my total afterwards. So I know that my final momentum is -2 kilogram meters per second, which is equal to mass times velocity. What's my total mass now? They're stuck together. So that's equal to 5 kilograms times my velocity. So the math problem we're working on here is -2 is equal to 5v. That's the math problem. How do you solve for v?
Divide by 5.
So v is equal to -2/5. So that's the math problem. So the physics of it is the velocity is negative, if you're a fraction or a decimal fan, we'll just -0.4 meters per second. Which means that after the collision, if they stick together, they will be moving in the negative direction, which is to your right. Questions to hear? Let's get rid of some of the stuff. And by the way, it's a closed system because it's just these two objects. There's no mention of any planet. It's just these two objects heading towards each other. So we'll start out again, and I've got my 3 kilogram object moving to the right at 4 meters per second. I have my 2 kilogram object heading to the left at, I think it was 5 meters per second. Do we want to stick with to the left is negative? Got a couple nods there. So to the left is negative. My initial momentum of the 3I. My initial momentum of the 3 kilogram mass. The subscript doesn't have to be, the mass doesn't have to be 3 and 2. I'm doing that just so that later on, if I have a subscript 3, I know I'm talking about this one. Subscript 2, I talked about that one. This, as we just did, is -12 kilogram meters per second, and P2 initial is 10 kilogram meters per second. So P initial is -2. This is what we had just done, just hopefully slightly neater. All right, so this time after the collision, they're not sticking together. After the collision, the 2 kilogram mass is heading to the right at, we'll say 6 meters per second. And the 3 kilogram mass is doing something. I don't know what the velocity, I want to find out what is the final velocity of the 3 kilogram mass.
What would that be?
Go ahead.
So the first one would be -12, right? 2 kilograms.
Oh, the 2 kilogram mass one?
Yeah.
All right.
This is heading in. Right.
All right, so P2 final, -12.
So the other one has to be.
momentum of this one, therefore. And how'd you get that have to be 10?
Because the momentum has to stay the same as the.
Yeah. So what am I gonna add to negative 12 to get negative 2? I know my final is negative 2, and this takes up negative 12 of it, so that has to be something that will add to negative 12 to get me negative 2. Probably should have picked different numbers, because, but we're here now. All right, so that's 10. And that's gonna be equal to the mass times the velocity of 3 final. So the math problem we're working with here is 10 is equal to 3v. That's the math problem.
Three repeating.
Yeah, so 10/3, or on a calculator, 3.3 repeating. So my final velocity of the 3 kilogram mass final, 3.3 repeating meters per second. All right, I'm gonna do one more, then we'll talk about lab. Let's see. Yeah, we'll do this one. 3 kilogram mass heading to the right at 4 meters per second. Same as before, but this time the other one's gonna be a 1 kilogram mass heading to the left at 6 meters per second. Just to mix it up, we'll say to the right is positive. So